Welcome to The Explainer. Today, we're unraveling the structural mysteries of chemistry, and we're kicking things off with a pretty mind-bending everyday paradox. We interact with the physical world around us all the time, right? But we rarely stop to think about how the completely invisible arrangements of atoms dictates literally everything we see, touch, and experience.
So let's dive right into this bizarre reality. Think about how 100% pure carbon can behave in completely opposite ways. Seriously, just think about it for a second. On one hand, you've got pencil lead. It's so incredibly soft that it just flakes off onto a piece of paper simply by dragging it across the surface. But then, on the exact other hand, you have a diamond, a gemstone so impossibly hard that it's literally used on the tips of industrial drill bits to cut through solid rock. Yet, they're both made entirely of carbon atoms. Absolutely nothing else. So how in the world is that even possible?
Well, the secret lies in a phenomenon called allotropy. Basically, this means if you take the exact same atomic building blocks, but you just arrange them differently, you get a completely new structure with brand new physical and chemical properties. It's exactly like playing with Legos. Imagine you have a massive pile of identical gray Lego bricks. You could snap them together to build this towering skyscraper. Or you could use those exact same pieces to build a wide, flat spaceship. The pieces themselves are 100% identical, but the final structure and what it can do is entirely different. In chemistry, we call these different structural forms of the exact same element allotropes.
To really prove this golden rule of chemistry, we're going to explore the fascinating allotropes of three different elements today. First up, carbon's many faces. Second, the oxygen twins. Third, shifting sulfur crystals. And finally, number 4, we'll wrap up by cementing our core theme, how structure dictates properties.
All right, section 1, carbon's many faces. Let's start with carbon, the ultimate shapeshifter of the periodic table, and finally solve that diamond and pencil paradox.
There are 4 incredibly important forms of carbon we need to look at here. We've got diamond, graphite, graphene, and a molecular cage with a ridiculously long name, Buckminsterfullerene, which thankfully is usually just called C₆₀. Now, keep in mind as we look at these, every single one of them is made of the exact same carbon atoms, just organized in completely different ways.
And this brilliantly illustrates our paradox. In a diamond, each carbon atom is strongly bonded to its neighboring carbon atoms, creating this rigid 3D covalent network that just locks everything tightly in place. Because its electrons are trapped in these bonds, it doesn't conduct electricity at all, and that rigid 3D structure makes it extremely hard. Now look over at graphite. The carbon atoms are arranged in a network of hexagonal rings, but they form separate, distinct layers. These stacked layers can slide over one another super easily, which is exactly why graphite is soft enough to rub off on your paper when you write. Plus, it has these free-flowing mobile electrons between those layers, allowing graphite to easily conduct electricity. It's the exact same element, wildly different structures, totally different properties.
Let's move to our next carbon allotrope and see how this builds directly on what we just learned. If we mentally zoom in on that block of graphite and painstakingly peel away just one single honeycomb layer from the stack, we get graphene. This single layer of carbon atoms, arranged in that hexagonal pattern, is a true wonder material. Because it's an isolated sheet, it possesses excellent electrical and mechanical properties that are quite literally revolutionizing everything from battery technology to flexible electronics right now.
Now, what's really fascinating is C₆₀, or Buckminsterfullerene. Unlike the massive continuous networks of diamond or graphite, C₆₀ is a molecular allotrope. It forms a literal discrete cage out of exactly 60 carbon atoms. It's shaped with pentagonal and hexagonal rings just like a classic soccer ball. And because it exists as these individual, uncharged football-like cages rather than one big extended lattice, its properties change entirely. It's stable under high heat and pressure, it actually dissolves in certain organic solvents, and it has a relatively low melting point compared to those massive covalent structures we just looked at. It's soft, and it really doesn't conduct electricity well. And again, this is just carbon.
Moving on to section 2, the oxygen twins. Let's look at our next element, oxygen, and see how this builds on our Lego analogy in a much simpler but equally vital way. The familiar oxygen we breathe in every single second, the gas we absolutely rely on for respiration and for fires to burn, is O2. This is simply a diatomic molecule, meaning it's just 2 oxygen atoms bonded together. It's the standard, everyday form of oxygen present right here in Earth's atmosphere. But what if we just add one more of the exact same oxygen atom to make O3? Well, we get ozone. This is a completely different triatomic gas. You definitely wouldn't want to breathe it in down here on the ground. But found high up in the atmosphere, its unique molecular structure crucially absorbs much of the sun's harmful ultraviolet radiation.
Just by snapping one more identical oxygen atom onto the molecule, we change it from the gas that fuels our lungs into the atmospheric shield that protects all life on Earth from UV rays. Pretty wild, right?
Next up, section 3, shifting sulfur crystals. Carbon and oxygen definitely aren't alone in this structural shape shifting. Let's check out our third example, which is sulfur's crystalline allotropes. When we look at pure sulfur crystals, we once again see allotropy hard at work. We have rhombic sulfur and monoclinic sulfur. Both are made of absolutely nothing but pure sulfur, but they arrange themselves into completely different crystal shapes. The yellow rhombic sulfur is the much more stable crystal arrangement under ordinary room temperatures. Monoclinic sulfur, on the other hand, has a different internal crystal structure and is noticeably less stable under those exact same ordinary conditions. The atoms are identical, sure, but the way they pack together completely determines how stable the crystal is just sitting there on a desk.
Which brings us to section 4, structure dictates properties. The absolutely crucial point here is that we've seen this exact same cause and effect relationship across 3 completely different elements on the periodic table. Looking at the big picture, a really clear pattern emerges. Whether it's the difference between diatomic oxygen for respiration versus triatomic ozone for UV protection, or layered conductive graphite versus a spherical solvent-dissolving C₆₀ cage, the structural arrangement always dictates the physical and chemical properties. The identity of the element? Well, that's only half the story. The architecture of the atoms tells the rest. Listen, if you take away just one thing from this explainer today, please remember this golden formula. The same element plus a different atomic arrangement equals a totally different structure which guarantees completely different properties. That right there is the golden rule of allotropy. All right, let's do a quick rapid revision to tie all these structural secrets together. First up, what is allotropy and what are allotropes? Well, as we've learned, the core of this entire phenomenon is allotropy, the ability of one element to take on multiple structural forms, which we specifically call allotropes.
Question 2. Why are diamond and graphite drastically different even though both contain only carbon? This is the exact reason behind our initial paradox. They're entirely different because diamond is locked in a super rigid 3D covalent network, while graphite rests in soft, sliding hexagonal sheets with free-moving electrons. Moving on, question 3. What is the exact molecular difference between O2 and O3? Simply put, it's just one single oxygen atom. But that one atom makes the difference between the diatomic O2 we breathe to stay alive and the triatomic O3 ozone layer that blocks solar UV rays.
Finally, question 4. Name the 2 crystalline allotropes of sulfur. That would be rhombic and monoclinic sulfur. And as we saw, the yellow, highly stable rhombic form behaves entirely differently than the differently shaped, much less stable monoclinic form.
Now that you know the chemical Lego blocks of our universe can be rearranged to create anything from the very air you breathe to unbreakable industrial diamonds, I want you to consider something for a second. Literally, just look around your room right now. Every single material you see, from the plastic on your desk to the glass in your window, relies on this exact kind of atomic architecture. So, what other structural secrets do you think are hiding right in plain sight, just waiting to be explored? Keep that curiosity alive, guys, and thanks so much for joining me on this explainer.